Hi guys. So today we're going to be going over some 8.2 key facts. So first I'm just going to start off on the right here and we're just going to go over the patterns or a lot of trends you'll see of polar graphs. And these are very important to remember. So the first one is an equation or the equation for a horizontal cardioid. So the cardioid looks something like this, kind of like a heart shape. And as you can see, it is sideways. And for horizontal cardioids, we associate that with cosine. And also, what makes it a cardioid is that these two, the amplitude and the vertical shift, are the same number. So they're the same value. For vertical cardioids, it's pretty much the exact same thing. R equals A plus or minus A sine of theta. So our amplitude and our vertical shifts are the exact same value. And it's the same shape, but you can see they're in that vertical form. All right. So then we have our equations for a horizontal limacon. I might be pronouncing that wrong. So just like the cardioids, the only thing different here is that our horizontal shift and our amplitude are not the same number. So that's what's going to determine if it is a limacon. And then horizontal, we associate with cosine. As you can tell, the petals are based horizontally. And the defining features of limacons is that there's technically two petals or two loops. We have our little loop right here and our big loop out here. Vertical limacon, basically the same thing. It's going to be our r is equal to a plus or minus b sine of theta. So we're associating with sine, and they look like this. So the petals and our loops being up and down in the vertical fashion. So then we have the equation of a rose. So for our roses, they are both associated with either, they can be formed with cosine or sine. So we see r is equal to a cosine n of theta, or r is equal to a sine n of theta. And n is just any real number. So 1, 2, 3, 4, etc. And so what n does is determine the number of petals on our graph. So if n is odd, then the number of petals is just going to equal that amount. So it's just going to equal n. If n is even, then the number of petals are going to be double n. So just to put that for into an example, if we have r is equal to sine 2 of theta, since 2 is an even number, we'll double 2 to get 4. And as we can see, we have 1, 2, 3, 4 petals. And then like for our odd ones, we see we have r equals cosine 3 of theta. So because 3 is an odd number, that means there will be only 3 petals. So 1, 2, 3. That proves to be true. Some other common polar curves are our circles. Technically, r is equal to a sine of theta and r is equal to a cosine of theta are roses, but just with only one petal because n is technically 1. So we only have the petal is just shown as a circle. What's important to remember with these two is that because they are technically roses, they are a circle, but they are not centered on the origin. So sine, you can see, if we remember, we associate sine with more our vertical. So you'll see it more on our vertical axis, our y-axis. And for r is equal to a cosine of theta, we'll see the circle more centered around our horizontal axis, which is our x-axis. And then for just a normal circle that is centered around the origin, we just have the equation r is equal to a. And so that's when you will have a circle centered around the origin. So then we have our straight line graphs. And so these are just any lines that are passing through 0, 0, so our origin. So the polar equation for these graphs is just theta is equal to a. And then technically they do have a rectangular equation for them, and that is just y is equal to tangent of that theta, x. So think of it like slope, y equals mx plus b. This would be the slope, and then we have our x. And then plus b is technically 0. There is no vertical shifts in these. So just for some examples, we would have theta is equal to pi over 2. Remember, pi over 2 is up here, so that would just be a straight line on our y-axis. And then any vertical line can be represented as an x equals, so that's how we get x equals 0 for our rectangular graph. If we have theta equals pi, we know that pi is right here, so it would just be a horizontal line where pi is, so on our x-axis. And then for the rectangular equation, we would represent that as y equals 0, because y equals always represents a horizontal line. Remember, these pass through the origin, so that's why it's 0. And then theta is equal to pi over 4. So the way you would graph this is that we know that pi over 4 is in our first quadrant. So this would be the angle pi over 4 here. And then if we just extended that line throughout, that's how we would get our line. And then just to solve for the rectangular equation, we see our y is equal to square root 2 over 2x. Square root 2 over 2 is just solved by doing tangent of pi over 4. All right. Now that we've done that, let's talk about the general process to actually graphing our polar graphs. So there's usually 2 general steps. The first step that you're going to want to do is you'll be given a polar equation. And so you're going to want to graph that equation as if we were in the rectangular coordinate system. So you would graph y is equal to f of x after you just replace r as y and replace theta as x. So if it was, and actually we'll get to examples of that. Step 2 is in our polar coordinate system. So once we have graphed it in rectangular coordinates, you're going to graph our actual polar coordinate by interpreting the x value as an angle in standard position and y value as an oriented distance between the pole and the point. So remember, with our oriented distances, we want them to be positive. And if we ever have a negative oriented distance, remember, that's when we have to go opposite of the angle. And we'll show that more in solving for the example of solving a Laracon. All right. So we are given r is equal to 1 minus 2 cosine of theta. So our step 1 is to graph it in rectangular form. So you see, all we just do is replace r of y or y with r and x with theta. So we get y is equal to 1 minus 2 cosine of x. So if we just rearrange that, it can also just be written as y is equal to negative 2 cosine of x plus 1. So what we know, 2 is our amplitude. We have a negative sign here, so that means there's been a vertical reflection. And then the plus 1 means we have a vertical shift up 1. So to find our maximum and minimums, we'll take our amplitude plus our vertical shift, because our vertical shift is positive in this case. So our maximum is 3, and then our minimum, which it would normally be negative 2, we'll add 1 to that, and we get our minimum of negative 1. And then our period is just going to be 2 pi, because remember, to solve for period, it is 2 pi over k. In this case, k is equal to 1, so our normal period is just 2 pi. So a lot of what's going on in this graph is something we'll need to analyze later, but just to analyze the basis of the graph, because cosine is negative, we'll start at our minimum and then go up. So here's our new midline at 1. So we'll have a point here, a point at pi, point at 3 pi over 2, and a point at 2 pi, and then so on and so forth. So that's how we get this lovely shape here. And I'll explain this in a second. So let's talk about step 1.5, it's just a little half step. So in this case, we're going to solve for the intersection points, which are our zeros. So wherever the graph crosses the x-axis, we want to know at what point is it crossing the x-axis. The reason why we're doing this is to help determine what our loops of our graph in polar coordinates will look like. So the way we do this is we're just going to set our equation equal to 0 and then just solve for x. So we have 0 is equal to 1 minus 2 cosine of x. If you hold on 1 second. Oops, sorry, I just realized I did 2 steps in one. So I subtracted 1, but then got rid of this negative sign off the 2. So we got 1 is equal to 2 cosine of x. And then we divided the 2 over and got 1/2 is equal to cosine of x. So we're just going to solve for 1/2 cosine of x. We know that cosine is only positive in quadrant 1 and quadrant 4. So we have, and the angle that solves for that, we use our reference angles, is pi over 3. So in quadrant 1, that would be pi over 3, and in quadrant 2, it would either be negative pi over 3 or 5 pi over 3. Therefore, those are our intersection points. So our step 2 is to now graph it in polar coordinates. But part of step 2 is actually interpreting our graph. And so that's what all of this wonderful colors and lines and stuff are. And so let's delve into this a little bit. So first, let's talk about how I've written loop. So for this case, I really only drew the graph starting at 0 and then ending at 2 pi. So that's really just what we're going to focus on, because that's our period for cosine. So I notice here that when the graph crosses our x-axis and then goes and crosses it again, that is when we'll have loops involved, is when there has been a change in the value, the distance. So this is our negative oriented distance down here, because we're in the negatives below the x-axis, and then on the top is our positive. So since we've gone from negative to positive, we'll have one loop. And then down here, we go from positive to negative, meaning we'll have another loop. So this loop will be the bigger loop because it goes from just 0 to 3, so that's just an increase of 3. And then this would be our smaller loop because it only technically goes from 0 to -1, and that's only a 1 unit distance. So this would be inherently our smaller loop. And there is technically a loop that happens right here as well. So now, what are all these fun colors? So these are going to be the steps in which we draw our graph. Usually we like to go from, when we're drawing the points on our graph, we're just going to go from point to point, one point to the next point. However, when we have intersection points, we want that we're going to include that as a point. So starting at 0, we are at our minimum. So we have 0 and then -1. And so this will be one part of the graph, and then this section is going to stop at our first intersection, pi over 3. And then to our next point on the graph would have been at our midline, so at pi over 2. So our second part of the graph that we're going to draw is going to be from pi over 3 to pi over 2, going from 0 to 1. Then the third part of our graph is going to be going from pi over 2 to our maximum at pi, so from 1 to 3. And then our fourth part of our graph is going to be going from our maximum from pi to 3 pi over 2. So from 3 down to 1. And then the fifth part of our graph is going to be going from 1 to our intersection, because remember we have to include our intersections. So from 1 to 5 pi over 3. And then our sixth and final part of our graph is going to be from our intersection 5 pi over 3 at 0, decreasing to our -1 at 2 pi. So let's put this all into perspective. And I'll try and keep this on here, showing this graph on the bottom so that you can see. So step number 1. All right, so we have 1 here. So this is happening between 0 and pi over 3, and our graph is increasing. It's going from 0 to, or -1, 0. But unitly, it's increasing. So since the function is negative, because this is below the x-axis, we're going to have to follow the opposite angles, because whenever we're below, remember when we're talking about our orientated distance, we don't like negatives. So we're going to have to go the opposite direction when we're talking about negatives. So instead of going from 0 to pi over 3, the opposite of 0 is pi, and the opposite of pi over 3, so here's 0, the opposite is pi, and the opposite of pi over 3 is 4 pi over 3. So if we start here, and I kind of highlighted it, and try and include it. So we start at our 1, and then it increases to 0. And we see we're going from pi, we're starting on the pi axis, and then ending, this is like the 4 pi over 3 line, so we kind of end at the origin since it is also 0. So then our step 2 is going from pi over 3 to pi over 2, going from 0 to 1. Since we are now above the x-axis, we are just going to follow that in itself. We're going to go from pi over 3, so this angle line right here. So we have our point here because it's at 0. And then at pi over 2, it's equal to 1. So we're going to go up to pi over 2 and 1. So that's how we get this line of the graph. So that's our second part. We talk about step number 3. We're going from pi over 2 to pi, and we're increasing from 1 to 3. And since this is above the x-axis, we are in our positive distance. So that is the trend we're going to follow. So we have pi over 2, and then we have pi over here, and then we have our 3. So we go this way around, and that's how we get that side. And then step number 4 is going from pi to 3 pi over 2. Here, pi to 3 pi over 2, but we're decreasing from 3 to 1. But we're still in our positive, so we're still going to follow pi to 3 pi over 2. So here we have 3 at pi, going down to our -1 at the 3 pi over 2 axis. That's how we get that side length. Step number 5 is going from 3 pi over 2 to our intersection point, 5 pi over 3. So going from 1 to 0. So we have our 1 at 3 pi over 2, and then we're going to 5 pi over 3. You can see that's right here, and that hits at 0. And then our final and last step, we're going from 5 pi over 3 to 2 pi, but we are in negative distance again. So we're going to have to go opposite. The opposite of 5 pi over 3, so here's 5 pi over 3. The opposite is 2 pi over 3. And then the opposite of 2 pi is pi. So we're going to go from 2 pi over 3 to pi. So we have our 2 pi over 3 here at our 0, and then at pi back to 1. And then we've completed our graph. And I have all the steps written out if you want to see them. Otherwise, I hope this helped. Thanks.